Okay, so in this lecture we'll talk about oscillatory motion and simple harmonic motion. So what is an oscillation? So oscillation is any motion that proceeds back and forth over the same path. Okay, for example, let's say you started from some point and you walked from point A to point B, and then you came back again at the same point, and then you moved to point B again, and then back again to A, move to point B and back again to A. So this kind of back and forth motion is called oscillatory motion. And not all the oscillatory motions are periodic. Okay, periodic means, let's say it takes time t to go from A to B and then back to A. Okay, so in the first instance you may take, let's say 2 minutes to go from A to B and back to A, and then in the next instance you may take a different time, so you may take 1 minute in the next instance to go from A to B and then back to A, and in the next instance you may take 4 minutes to go from A to B and then back to A. So this is non-periodic motion. But there are some motions in which the oscillation is periodic. Okay, so you take exactly same time to go from A to B and then back to A. Okay, if that's the case, then this kind of periodic motion in which the time period is always same is called simple harmonic motion. Okay, so simple harmonic motion is an oscillatory motion in which the period of oscillation is always same. Okay, so let's see an example of this kind of oscillatory motion. So this kind of oscillatory motion in which the period is always same. Like in this example, you have a ball that is disturbed from its equilibrium position. Okay, so this ball has this equilibrium position. As long as there is no disturbance, the ball will remain in this position, which is the stable equilibrium position. But if you slightly disturb this ball, because of this net force, the ball will move back to its original state or equilibrium position. Again, the marble that is free to roll inside this spherical ball has this equilibrium position, which is the bottom of the ball, where it will rest with no net force on it. But if the marble is pushed away from equilibrium, the marble's weight, okay, this weight leads to a net force. A part of this, a component of this weight will provide the net force, which is directed towards the equilibrium. So this acts as this net force. Again, this net force comes from the weight, acts as a restoring force that restores it back to the equilibrium position. Okay, so when it's moving towards the equilibrium position, it will overshoot and it will go to the right side, and then again there would be this net force pointing to the left that will bring it back again to the equilibrium position, and then it moves to the left, and then the net force brings it back to the equilibrium, moves to the right. So it does this back and forth over and over, and this kind of oscillation happens in equal time interval. So it's a simple harmonic motion. Okay, so this is an example of simple harmonic motion. And this kind of simple harmonic motion is described by a sine wave, or any kind of simple harmonic motion can be described by a sine wave that you have already seen in lab. In case of lab, we had this spring with a block, and we saw that this block moved up and down at some time interval, which is also a simple harmonic motion. So simple harmonic motion is described by this sinusoidal function or sinusoidal equation, which is a sine omega t plus phi. So here this y is the displacement of the object from its equilibrium. So this y gives us the displacement at some time t. Okay, let's say you want to find where this object is in 2-second time, whether it's here or here or here. So that's given by this equation. Okay, and this equation, this a is the maximum displacement. Okay, the farthest it can go. So this is, if this is the farthest it can go, then this is the amplitude. Like in case of spring, let's say the spring can go up to this point, okay, from its equilibrium, then this would be the amplitude. So that's amplitude, and omega is the angular frequency. It's also called angular velocity. Angular velocity. Okay. So again, we have W as angular, let me rewrite the equation. I already erased that. So y is a sine omega t plus phi. So here omega is angular frequency, and angular frequency is related to the linear frequency. Linear frequency is how many times does it do this up and back and forth. Okay, so it starts from here, moves up, and then back again to the same equilibrium, and then to the left, and then back again. So that's one oscillation. So again, one oscillation is moving from here to here, and then back again to that point, and then to B, and then back again to the same point. So that's one oscillation. So frequency is how many such oscillations are completed in 1 second. So number of oscillations per second, and the angular frequency is given by 2 pi omega. Okay, angular frequency is how much angle it makes in 1 second time. Okay, so this is also angular velocity. And we also know the time it takes to make one complete oscillation is time period. So t is time for one oscillation. So the relationship between time period and frequency is 1 over t. Okay, so this equation is basically a sine equation. So that's displacement from the equilibrium, and this is time. So this distance is amplitude, and the time to make one complete oscillation, this from starting from here to here, is one complete oscillation. That is the time period. Okay. And frequency is basically how many such complete cycles are made in 1 second. Okay, number of oscillation per second. So now we talked about this spring mass system in our lab. So for a spring mass system, when it's oscillating under gravity, when it's moving up and down, so its time period is given by this formula. It's 2 pi square root of m over k. So here m is the mass of that object, hanging mass, or sometimes it could also be on the horizontal plane. In that case it's not hanging, okay, it's just the mass attached to the spring. And k in this case is the spring constant. Okay? Spring constant, we already talked about this in the previous chapter. What spring constant is, it basically tells us how stiff the spring is. Okay, and again this formula gives us the time period of this spring mass system, and if I want to find frequency from that, I can just use 1 over capital T, which would be reciprocal of that, so 1 over 2 pi k over m. And if I want to find omega from that angular frequency, then it's 2 pi f, so which would be 2 pi f is 1 over 2 pi k over m. So omega, or angular frequency, is, so cancel 2 pi and 2 pi, you get k over m. Okay, so with that, now we can solve some numerical problems. We'll look at some numerical problems, and then we'll also see some of the homework questions. So let's look at question. So a 51.8 kilogram bungee jumper jumps off a bridge and undergoes simple harmonic motion. If the period of oscillation, so its period is 11.2 seconds, what is the spring constant K? And mass of the bungee jumper is 51.8 kilogram. So the time period of the oscillation is given by 2 pi m over k. So we can, in order to find k, we can square on both sides, then we get t squared is 4 pi squared, mass is 51 point, by the way we are squaring, so squaring the square root will cancel that square root, so then we'll have m is 51.8 kilogram over k. Okay, so we want to find k. So multiply both sides by k, you get t squared k is 4 pi squared times 51.8 kilogram, and then divide both sides by t squared. Okay, cancel t squared and t squared, so k is 4 pi squared 51.8 kilogram, and then t is 11.2 seconds. Okay, that's squared. So calculate that, that will give you k. K is measured in Newton per meter. Okay. Now let's look at another problem. So a simple harmonic motion oscillates with frequency f when its amplitude is a. If the amplitude is now doubled to 2a, what is new frequency? Okay. So we saw, this is a conceptual question, we saw this in lab. So we found that amplitude does not affect the frequency. Okay, that's what you should have seen in the lab. Okay. So that means even if you double the amplitude, the frequency will still be f. Okay. Let's look at this question. So we have this mass spring system that undergoes simple harmonic motion. When the mass is at the maximum distance from equilibrium, which of the following statement about it is true or are true? Okay, there could be more than one answer. So speed is 0, acceleration is 0. Acceleration is never 0 in simple harmonic motion. Okay, because of that, the object always is restored. So the object moves down, 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 but because of this restoring force, which has the restoring acceleration in the upward direction, it moves back. Okay, after reaching some maximum point, it goes back, and again it moves up, 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 up. And when it's moving up, there is this acceleration in the downward direction, because of which at some point it stops and then moves back. Okay, so there is always acceleration present in this case, due to which the spring moves back and forward. Otherwise, if there were no acceleration, then it will just stop, or it will not move at all after some time. Okay, so that's not true. Its speed is 0. So we saw in the lab that, so you might have seen the graph. So starting from this equilibrium, you displace it to some distance, and then it speeds up, speeds up, speeds up, speeds up. It will have the maximum speed at this point, at the equilibrium, and then it slows down, slows down, slows down, and it stops after reaching the maximum point. Okay, and then it goes back, speeds up, maximum speed, and then slows down, and stops. Okay, so that happens all the time. So that means this is true. So the speed is 0 at the maximum distance. Okay, maximum distance from the equilibrium, here and here, speed is 0. Its elastic potential energy is 0, which is not true, because elastic potential energy depends on how much you stretch. Okay, this x. So more the stretching, more is the potential energy. So that's not true. Its kinetic energy is maximum, which is not true, because kinetic energy depends on the speed. If the speed is 0, then kinetic energy cannot be maximum. It should also be 0. So that's not true. The total mechanical energy is 0, which is not true, because total mechanical energy is always constant. If you have some mechanical energy, no matter where the object is, whether it's here or here or here, total energy always is conserved. Okay, it's constant. So that's not true. So the right answer is B. Okay, now let's look at next problem. So we have a 0.415 kilogram mass suspended from a spring, undergoes simple harmonic motion with period of that. How much mass in kilogram must be added to the object to change the period to 1.75? So you have this spring mass system. Okay, for this mass of m1, the period is 1.25. Now you added some mass on it. Okay, this is now a little bit heavier, so that's called m2, where m2 is m1 plus some additional mass. So for that, time period is now 1.75 second. So we want to find the additional mass, which is m2 minus m1. Okay, so for the first one we can write t1 is equal to 2 pi m1 over k. The spring is same, so it doesn't say we are using different springs, so we can just use same time spring constant k. So for t2 it's 2 pi m2 over k. So we can divide the two equations term by term, so t1 over t2. We want to find m2, so let's divide t2 by t1, second equation by the first equation. So t2 over t1 is equal to 2 pi m2 over k. 2 pi, that term is m1 over k. So let's take the square on both sides, so t2 over t1 square, 2 pi and 2 pi cancel, so square root of m2 over k, square root of m1 over k square. So this square and the square roots cancel, so m2 over k, m1 over k, so k and k cancel, so we have m2 over m1. So we want to find m2, so m2 would be m1, multiply both sides by m1, so you get m2 is m1 times t2 over t1 squared. Okay, and then you can substitute the given values. So m1 is 0.415 kilogram, and then t2 is 1.75 second, and t1 is 1.25 second square, so that will give you m2 kilogram. And then to find the additional mass, which is delta m, the mass you need to add to change the time period to 1.75 seconds, that would be m2 minus m1. Okay, okay. So that's from the homework problem. Now let's look at another question. A diver on a diving board is undergoing simple harmonic motion. So that's the diving board. Okay, it's going simple harmonic motion. Our mass is 51.5 kilogram, and the time period of oscillation is 0.75 second. And using on the same board, okay, another diver undergoes simple harmonic motion, but for this person, let's say his mass is m2, which is unknown. The time period is 1.015 second. Okay, so what is the mass of this person? It's exactly the same kind of problem like we did in the previous one. So t1 is 2 pi m1 over k, and t2 is 2 pi m2 over k. So divide equation 2 by equation 1. So t2 over t1 is equal to 2 pi m2 over k over 2 pi m1 over k. Okay, So square both sides, can cancel 2 pi and 2 pi, so we have t2 over t1 squared, that's equal to m2k over m1k. Okay, we are cancelling the square roots and the square, so can k cancel, so m2 dividing multiplying both sides by m1, we get rid of this m1, so that will give us t2 over t1 squared times m1. So t2 is 1.015 second, t1 is 0.75 second, that's squared, and the mass of the first person is 51.5 kilogram. Okay, and do the math, you will get the mass of the second person. Okay, so let's look at another question. Near the top of the Citigroup Center building in New York City, there is an object with mass of 3.2 times 10 to 5th kilogram on springs that have adjustable force constants. Its function is to dampen wind-driven oscillations of the building by oscillating at the same frequency as the building is being driven. The driving force is transferred to the object, which oscillates instead of entire building. What effective force constant should the spring have to make the oscillation with a time period of 1.2 seconds in Newton per meter? What energy is stored in the spring for 1.2 meter displacement from its equilibrium? Okay, so this is pretty straightforward if you know the equation. So we want to find the effective force constant. So force constant here means the spring constant. Okay, it's k. To find the k. The time period again is 2 pi mass over k. We want to find k, so you can take square on both sides. So 4 pi squared m over k, and then multiply both sides by k. So k and k, so you can cancel k and k, and then also divide both sides by t squared just to get rid of that on the left. So then k would be 4 pi squared m over t squared. Okay, so 4 pi squared, mass is 3.2 times 10 to 5th kilogram over time period is 1.2 second squared. Okay, so you do the math, that will give you the spring constant in Newton per meter. And then what is the energy stored? So we know from our previous chapter, the spring stores potential energy, which is given by this formula. So potential energy of a spring, either compressed or stretched spring, is 1/2 k delta x squared. So 1/2 k is whatever you find from here, that's the k, and delta x is the stretching or compressing of the spring. So in this case, the spring is compressed by 1.2 meter. Okay, that's squared. So that will give you potential energy in joules. Now let's look at another question. A 75 kilogram person is bouncing on a bathroom scale which has a force constant of 1.25 times 10 to 6th Newton per meter. What is the maximum velocity of the person in meters per second if the amplitude of the bounce is 0.115 centimeters and what is the maximum energy in joules stored in the in the spring. So we want to find the maximum velocity. So what we need to do here is to find the maximum velocity. Let's say that's the spring. Okay, so that's the spring of the bathroom scale, and it's doing this bouncing. It's bouncing back and up and down. Okay, it's compressed and then it's elongated or extended. So here, to find the maximum velocity, we want to use conservation of energy. So when the spring is at the maximum displacement position, its displacement would be amplitude. Okay, so that's the equilibrium. Okay, so it's stretched. Okay, it goes up to here. So this is the amplitude, the maximum displacement, and during the stretching, its energy during maximum amplitude, that would be equal to energy at any other instant. Again, like I said before, no matter where the spring is or what the configuration of spring is, its total energy is always same, because energy is conserved. Okay, so whether it's stretched like that or whether it's compressed like that or whether it's in equilibrium, it's always same. So that means we know the energy in the stretched condition, this maximum stretched condition, is only that of the potential energy. There is no kinetic energy, because at the maximum displacement it momentarily stops, so there's no speed at that instant, so there's only potential energy. So this is only potential energy. So potential energy is K extension delta x. In this case, delta x is A, so A squared. And at other instances, it's the combination of kinetic energy and potential energy. Okay. Now kinetic energy is 1/2 mv squared, and potential energy is 1/2 k delta x squared. Okay. So we can cancel half and half. So we want to find V, so let's write this equation in terms of V. So we have Ka squared here, take this to the left, so that would be K delta x squared, that is equal to mv squared. So K and K common, you can take outside the parentheses, so A squared minus delta x squared, that is equal to mv squared. And then K, this m, divide both sides by m, you get K over m. Okay, A squared minus, this is the displacement, and for simple harmonic motion, displacement is given by this formula, A cosine or sine omega t plus phi. Okay, or you can just write, just suppose we don't care about that. So this is basically tells us where the this curve starts. If it starts from 0 point, then this phi is just 0. Okay. If it doesn't start from 0, like it starts from, let's say, a little bit before 0 or a little bit after 0, like that, then in this case this phi is this distance, okay, where it starts. But let's assume that in this case the curve starts from 0 position of this sine wave. So this is the displacement, okay, and this y is basically when it's the vertical displacement, when it's moving up and down. But in some cases the spring may also be moving back and forth like that, okay, right and left. In that case, instead of x we just write, instead of y we just write x, so x a sine omega t. Okay, so we can replace our delta x by that a sine omega t. So delta x squared, okay, is a squared sine squared omega t is equal to m. We already got rid of m, divided both sides by m, so that's v squared. So k over m, as squared and a squared are common, so put it out. So 1 minus sine omega t, sine squared omega t is v squared. So to get rid of square we need to square root on both sides. Let's do that later once we simplify this. So k over m a squared, so 1 minus sine squared theta is cosine squared theta, okay, cosine squared omega t. Now let's take square root on both sides, so that's square root and square cancel, this square and square root cancel, and that cancel, so we get v is equal to a k over m cosine omega t. And I showed in the very beginning that this thing k over m is omega. Omega is k over m. Okay. So this is the expression of velocity at any point, okay, or speed at any point during the simple harmonic motion. Given by a omega cosine omega t. But now we want to find the maximum velocity, okay, so here we are looking for maximum velocity, and we get the velocity to be maximum when this cosine omega t is 1. I mean, cosine omega t can have any value between 0 to 1, and this won't give us the maximum value, or anything in between won't give us the maximum value. But we have, if we have cosine omega t to be 1, then that would be the maximum value, okay. So you can just keep substituting different numbers for cosine omega t, but if you substitute this to be 1, that will be the maximum value. So v max would be a omega. Okay, so we want to find that. Again, a omega is again k over m. Okay, k over m. So let's plug in the numbers. So v max is, so let's see, we have a is 1.115 centimeters, so centimeters is 10 to negative 2 meters, and then square root k, force constant is 1.25 times 10 to 6 Newton per meter, over mass is 75 kilogram. Okay, so when you do the math, you get the maximum velocity. Okay, and then the next one is, what's the maximum energy stored in the spring? So energy stored in the spring is given by this formula 1/2 k delta x squared, and maximum energy would be when the spring has the maximum amplitude, or maximum displacement, which is the amplitude. Okay, so let's say this is the equilibrium. So when you stretch it, it will have more and more potential energy, and at the maximum displacement it will have the maximum potential energy, no kinetic energy, just the potential energy, and the distance corresponding to that is the amplitude. Okay, so here this thing would be this would be A, maximum displacement. So potential energy max is 1/2 k A squared. So 1/2 k is 1.25 times 10 to 6 Newton per meter, and then A is amplitude, which is 0.115 times 10 to -2 meters squared. Okay, so that'll give you potential energy in joules. Okay, that's all for this lecture. You should be able to do all the homework problems with this concept. If you guys have any question, please feel free to email me. Okay, let me know. I would be more than happy to help.